Welcome to this video in Mathematics 2. In this quick video, I'd like to give you a few examples of multivariate functions as they appear in economic models. So that you see that this theory actually has an interesting application in economics. So we'll be talking about examples of multivariate functions in economics. And of course, the reason why multivariate functions play an important role in many economic models is that there are often a lot of factors influencing a certain outcome. You cannot possibly hope to capture all of these factors usually, but of course you'd like to at least capture the most important ones and not just one single factor. That's just not sufficient for most of the models that we know. So I'll present you two models that you probably know from other lectures already, maybe in different notation, but that shouldn't be a problem. Just to give you an idea of why multivariate functions are important in economic applications. The first function I'm going to talk about is Keynes consumption function. And the idea of that function is to model the consumption as a result of an individual's disposable income. So according to John Maynard Keynes, who more or less invented that model, consumption of an individual is directly related to disposable income. Okay, what I'm going to present to you is a pretty simple version of that model. Of course, there are versions that involve a lot more factors, but I'm just going to give you the rough idea here. So the idea here is to model the consumption of an individual C, basically as being composed of one factor that we call C0, that is autonomous consumption, so consumption that just needs to happen. You need to eat, you need to drink. There is some consumption that is unavoidable to be able to survive. And then there's consumption that you can choose to spend or not. And of course, what you choose to consume will depend on the income that you have available. And in this simple version of the model, Keynes simply says an individual will spend a certain amount, a certain percentage of his or her disposable income. So the consumption is composed of this autonomous part and a part beta times I, where I is the disposable income, and beta is what is called the marginal propensity to consume. So C here, that is the consumption. C0, that is the autonomous consumption. This I is the disposable income. And beta is the marginal propensity to consume. And again, this is a very simple version of the model. For example, it's not that clear that the relation is really linear. It's probably capped somewhere. And then there's also factors that influence that better. So that's a really simple idea, but I'm just going to talk about this idea and how it relates to multivariate functions, what can be done in economic theory about this model and more complicated models in general. So the problem here usually is there are several variables in that model that you can measure. For example, you can pretty easily measure the disposable income of an individual. And you can also measure the consumption by some means. What you don't know usually is autonomous consumption, and what you also don't know is that beta. So one possible question that economists ask is, how can we determine the autonomous consumption, and how can we determine this marginal propensity to consume for a given society, so that we maybe can compare the societies based on these factors here. So problem is, while C and I can be measured, C0 and beta need to be determined indirectly. So what you do is you take a large amount of measurements and then you try to infer C0 and beta from that. So you do a large amount of measurements, and you have a long list of measurements, C1, I1, C2, I2, and so on, up to some Cn, In. And then you want to infer C0 and beta. From these measurements. Now, of course, in theory, this is a linear equation. So a linear equation, two unknowns, so two measurements will provide you with two linear equations, and that should be sufficient to solve for C0 and beta. But of course, there may be a lot of other factors that this model does not actually capture. So if you just do this, your whole theory, your whole idea of these factors depends on two more or less randomly chosen individuals. And this might be error prone. So what you would like to do is you'd like to take this large amount of measurements that you have and find a method to infer C0 and beta that more or less fits all of these measurements. Okay, so the idea here is to say that, well, for all of these individuals, for all these measurements, the following relation holds. The consumption CI is governed by that model, so it's C0 plus beta times capital II. And then there is some error term for that individual, let's call that epsilon I, that we don't really know. There might be other factors that somehow determine this error term here, and that's different for every individual. And of course, we'd like to be able to explain the majority of all of these measurements, not using the error, but using our actual model. So we'd like to choose C0 and beta such that the error becomes as small as possible. So the goal is to find C0 and beta such that the errors become as small as possible. And these errors are kind of what the model cannot explain, what the model does not capture. We want this to be small, of course. Okay, to be more precise, what we want is as small as possible. What that means is we want the sum of all these error terms to be as small as possible. And of course, an error could be positive or negative. It could be in both directions. And we don't want that to cancel out. Yeah, a negative error is just as bad as a positive error. It's not that one negative error and one positive outweigh each other. So we'd have to take something like the absolute values of these. Unfortunately, absolute values are not very convenient mathematically because that is not a differentiable function. So what you'd usually want to do is you'd square these errors. That gives you something that is differentiable, that is nicely, can be nicely treated. And we want to minimize that sum of squares. Okay, this is what is known as a least squares regression. So we're trying to fit parameters for a linear function such that the sum of squares of errors is minimized. That's a least squares regression. So that leads to the following function. What we have here is we want to minimize the function sum r equals 1 to n of the ci minus c0 minus beta times capital I squared. Because this expression in here, this is precisely the error of that ith measurement. Okay, and that is a function that depends on two parameters, c0 and beta. The capital Ci and the capital II are known. So we get a function that depends on two variables, and we want to minimize that. So I want to minimize a function f r squared to r. So basically, the determination of these parameters, that leads to an optimization problem of a multivariate function. And that's an application that comes up very, very often in economics. You want to be able to determine parameters of an unknown model, and there's usually more than one parameter, so you need to optimize a multivariate function. I'll give you one more example. Same idea, just a little twist to that. That's the so-called CobbDouglas production function. Again, that is a model widely used in economics. That models the total production as a function of labor and capital investment. Yeah, so total production as a function of labor and capital investments. And Cobb and Douglas, among others, hypothesized that this is best modeled through a relation like this. Why? This is the total production. So this total production is equal to some factor alpha that they call productivity. And then it depends on the labor input and the capital input. And a suitable model is a product of these two. And again, there are certain factors here. One factor, let's call it B. L to the B scales the labor output, and the capital input is also scaled by another factor. Let's call it A. Okay, so we have L, that's the labor input, K, that's the capital input. Then we have that factor alpha here, that's called total factor productivity. So that kind of scales the result of both factors. And then we have A and B. Those are called the output elasticities of labor and of capital, respectively. Okay, so A and B are so-called output elasticities of labor and capital. Basically, those model the amount of how much labor and capital determine what the actual output of the production is. Okay, again, there are certain terms that can be measured directly. Of course, the production could be measured, the labor input can be measured, and the capital input can be measured. What we don't know is alpha and A and B. Okay, so here Y, L, K can be measured. Alpha, A, B have to be determined indirectly. And again, this leads to a least squares regression. This is usually solved by least squares regression. Problem in this case is that the functions look pretty darn complicated here. So we have these exponential functions in here. I mean, this alpha is nice, yeah, but then you have L to the B, K to the A. So if you want to have a model that involves A and B and alpha, then there's exponential functions involved here. That's not very nice. So what you do is, in this case, you apply a logarithm to both sides. If you have a model like this, then that's usually the way to go. You apply the logarithm, that gives you log of y equals, of course, the log of alpha times L to the B times K to the A. And now you can apply rules of logarithms. So first thing we can do is we can split the product. The logarithm of a product is the sum of logarithms. So we get log of alpha plus log of L to the beta plus log of K to the A, sorry, L to the A, of course, K to the L to the B, of course, K to the A. So that's a lot easier. We don't have a product anymore, we have a sum. And it gets a lot better if we apply the rule that the logarithm of an exponential function can also be written in a different way. So that's an alpha, of course. The exponent can be put in front of the logarithm. So that's the same thing as b times log of L plus a times log of K. Right? And now you measure L, you measure K, you measure Y. So you can also get the logarithms of these inputs. That doesn't really matter much. And B and A now depend linearly on that. There's still this logarithm in the alpha that makes it somewhat inconvenient, but it's not that bad anymore. Yeah, so what you get in the end is again a function you want to minimize. You want to minimize the sum of squares of measurements. And again, those squares that you want to minimize are the squared errors of your measurement. So you have the logarithm of the yi, that's the measurement of the total production, minus the logarithm of alpha, minus b times the logarithm of li, again li is a measurement, minus a times the logarithm of ki, and again ki is a measurement. You square that. So what we get is this time a function of 3 variables, alpha, b, and a. So we have in effect a function from R3 to R that again we want to minimize. Okay, so same idea, it's just the logarithms that are involved to make this a little easier to handle. So as you can see, optimizing multivariate functions is an important task in economics, not just in economics. And we'll spend quite some time talking about how to optimize multivariate functions. But first we have to get an idea of how to properly define a differential as an important tool for that optimization. And that's what we're going to do in one of the next videos.